Here. I'm happy to have you on. Go ahead.
Thank you much, Peter. So thank you much for this invitation. I'm really delighted to be meeting this community. A very important administrative task to ask to everyone, can you see my slides? Yes, and I can see your thumbs up. So that is already a great form of interacting. So it's going to be probably a 45-minute talk. That's the amount of content, of raw content, that is if I were talking without interruption. But I welcome your interruptions and clarifications at any time, so please feel free to do so. And if I wanted to say a few words about myself, I would say I'm a bit of a jack of all trades. I have been working on different kinds of machine learning projects. When I was doing my PhD at NYU in New York with Professor Yann Lequin, I worked on epileptic seizure prediction from EEG, on motion capture data, and on text modeling and language models. Then I ended up doing some robotics at Bell Labs, as well as Wi-Fi-based geolocation and localization. And the robots were used in order to enable us to geolocalize ourselves and acquire data. I did a shorter stint at Microsoft Bing on search query autocompletion. And for the past 8 years, I've been working at DeepMind, mostly on reinforcement learning for navigation. However, in the last 3 years, I switched to this project related to climate and weather in particular, which is nowcasting, which means forecasting in a very short term precipitation. So I'm giving this talk on behalf of DeepMind and of our collaborators, the UK Meteorological Office. And I am delighted to present what essentially ended up being our publication, Skillful Precipitation Nowcasting using deep generative models of radar. So the work I do at DeepMind, which is a research lab in AI, is in various areas of science and involving AI. And like several of my colleagues, I am interested in the application of AI to the real world. And for this project, we needed a partner and additional expertise. So we joined our forces with the informatics lab at the British Meteorological Office, the Met Office in short, which was founded in 1854, and which has pioneered the science of meteorology. There is a little anecdote, which is that the Met Office is responsible for having moved D-Day from the 5th of June to the 6th of June 1944, because they had forecasted some unfavorable weather conditions for the Allies. So in this project, our aim was to combine the strengths of those two institutions, and we are both research-driven organizations, and we wanted to build a deep scientific collaboration. So we did meet on a weekly basis for a long time, over 2 years, and it was a very good learning experience for all of us. We started from initial meetings at the end of 2017, and then we explored different kinds of questions related to weather forecasting into climate. And we confronted two different approaches: machine learning and numerical weather prediction models. And we found that there was a sweet spot, precipitation nowcasting, that stood out as the perfect opportunity for applying machine learning techniques. So after a couple of years of research involving a long writing and revisions process, we managed to publish our work in Nature, and this presentation covers that specific work from a perspective of a researcher in machine learning, or a jack of all trades in machine learning. And the talk will basically consist in 7 small parts. The first one being the statement of the problem. So precipitation nowcasting. We know that precipitation nowcasting is the prediction at a very short time horizon, up to 2 hours into the future, of precipitation. And we do it at high resolution. This nowcasting is crucial for weather-dependent decision-making. because it can inform the operations of a whole variety of sectors, including flood early warning systems, air traffic control, marine services, emergency services, energy management, etc. And we believe that nowcasting is interesting from a data science perspective for three distinct reasons. First of all, for nowcasting to be useful in all those applications, the forecast must provide accurate predictions across multiple spatial and temporal scales. Second, the forecasts must account for uncertainty and be verified probabilistically. And uncertainty and probabilistic verification are going to be the very big themes in this presentation. Third, nowcasting to perform well needs to also perform well on heavier precipitation events, which are rare. So the usual rare event detection problem. And these rare events are those that affect critically human life and the economy. So our work, as you can imagine, based on the, you can have guessed based on the maps that you've been seeing, focus on the UK. And the nowcasting models that we built were trained and evaluated on data from a collection of Doppler radars acquired by the Met Office Radar Net4 network, which comprises more than 15 operational radars covering 99% of the UK and part of Ireland. We can visualize that data as a grid of 1500 by 1200 pixels, where each grid pixel of that composite image represents the surface level precipitation rate over a region of 1 kilometer by 1 kilometer. And it is expressed in millimeters per hour. To give you an idea, 30 millimeters per hour would be a pretty heavy rain. 100 millimeters per hour, which is 1 meter per hour, is something that can happen over the frame of a few minutes, and it is extremely rare. The imperceptible rain is typically at 0.5 millimeter per hour. That little rain that just is enough to drench you after a few hours. The UK uses a custom projection system and a coordinate system that is centered on the UK. So it's as if you had shifted the equator to be crossing somewhere in the middle of the UK, in the Midlands. The animation that you can see here is showing a complex rain phenomenon with convective initiation of rain. So convective initiation meaning evaporation, essentially, and formation of rain clouds. And then there are strong gusts of wind coming from the west that are pushing the rain clouds towards the northeast, with downpours and drenching rain over Northern Ireland and Scotland, and mild showers over the rest of England. The Met Office data provisioning team gave us radar composite images every 5 minutes since early 2016. And that represents a few terabytes of data. So we are definitely in a big data regime. And I think we are facing also a deep challenge for video prediction, because we are dealing with 1 kilometer resolution images with a data set size that is dwarfing the size of MNIST digits or ImageNet samples that we've typically been playing on for a long time. Our method was also evaluated on a different data set, and that was to essentially check if we can generalize our techniques by retraining the model from scratch on data from the continental United States using radar composites from the multi-radar, multi-sensor MRMS system, acquired with a network of 146 radars covering the USA and about 30 Canadian radars, with a resolution of 0.01 degree, which is about 1 kilometer for each step of latitude. And it's between 1.1 kilometer for each step in longitude at the level of Florida, and 0.6 kilometer for each step of longitude at the level of Seattle. And this is because of the curvature of the Earth. So the image actually that you're seeing here, which is in equirectangular projection, is a complete deformation. And we know that when we look at maps of the world using the Mercator projection system or equirectangular projection system, they are giving a very false idea of sizes, relative sizes, and even shapes of continents.
We actually had a talk about this. I'll add a reference a couple of months ago exactly about the thing of if you go from a spherical representation to flat, how it changes and deforms the original shape. And it's and you can't go back also, you can't revert. It's like one-sided transformation.
Yes. So it was not a big deal for the UK data simply because, so as I said, 1,500 kilometers meant, and if you readjust the coordinate system so that the equator of that coordinate system passes by the middle of the UK, then that effect is really negligible. It's like a pixel out of 1,000 pixels. So it's basically 0.1%, I think. I mean, like, based on my calculations. But of course, it's a huge effect over the US, especially if you stick with the latitude-longitude system, coordinate system that and do not shift the reference system. So if you do not reproject. So back to that data set, MRMS, it was not actually as nice as the UK data. And that's not only because of hurricanes and scorching and sweltering summers or frostbite winters, something that we don't really get in the UK, even if some press sometimes talks about scorchers because it's 28 degrees Celsius. So what happens in the with the MRS data is that, first of all, it doesn't rain as much in the US as it does in the UK. So essentially, rain becomes more of a rare phenomenon prediction. Then we also noticed some skipping patterns in the way MRMS data were updated. So the data were theoretically sampled every 2 minutes. However, when we looked at videos of MRMS, we noticed that the updates were asynchronous between different parts of the US or different radars. So we actually had to smooth it out at the time scale of 6 minutes in order to remove that strange effect. So we reduced the temporal resolution to 6 minutes instead of 2, but this made is essentially aligned with the UK data set. So it was effectively a good design choice. At this point, I need to say a few words about the other possible data sets we could have used, which is coming from numerical weather prediction systems, first of all. So numerical prediction models are essentially simulations of the coupled physical equations of the atmosphere and the oceans, and they generate multiple realistic precipitation forecasts. You can see them as deterministic solutions to the Navier-Stokes equations, discretized over a grid, which can be a latitude-longitude grid of, at the finest possible level, 1 kilometer, but typically 3, 9, sometimes 150 kilometers, depending on the time scale under consideration. So NWPs, numerical weather prediction models, would have been natural candidates for forecasting because one can derive probabilistic uncertainty estimates. So the way that those uncertainty estimates are derived in numerical prediction models is that even though they are deterministic, what you do is that you change the initial conditions. And because it's a chaotic system, very highly nonlinear system, the initial errors can grow exponentially with time. And with changing the initial conditions, you can essentially change the outcome through that deterministic system.
So, sorry, you said it's okay to ask during the presentation.
Please.
Like, you used NWP models as a part of your predictors, or you did not?
No, we did not.
So now my question would be like, because my understanding is that those NWP models may have the actual forecasts for that 1 hour or 2 hours.
Yes.
Like, so
Why we didn't know?
Yeah, exactly. That's my question.
Exactly. So that was exactly the following sentence in my talk. So what happens is that numerical prediction models need to go through a phase of data assimilation with actual real observations. So you need to reconcile the initial conditions with the actual observed state of the atmosphere and the oceans, and you can do it only by taking observations using a collection of weather stations or satellite data. But that data assimilation is never actually perfect. And so what happens is that in the first 2 hours, 2 or 3 hours, you have a double problem. First of all, the data assimilation itself is a computationally expensive process. So let's say that you get radar data up to noon. And then you start the data assimilation process of the numerical prediction data, which would take already a couple of hours. So by the time you have finished the data assimilation process, already 2 hours elapsed. And then you have an imperfect estimation of the state of the atmosphere. Because it will be a bit like an interpolation between the prior of the NWP state and the actual observations, which themselves are noisy.
So I guess like the main issue was the latency, like that.
Yes, it's the latency and also the imperfection of the model. The model really starts shining after 3-4 hours, where it is able to be run up to 2 weeks, 14 days, and give very good longer mid-range weather forecasts, which are based both on the physics of the atmosphere and the oceans and also on the observations. But there is, and that's really the sweet spot where we intervened, there is this first 2 to 3 hour gap between the actual observations of radar and the NWPs. So that's where we used machine learning models directly on radar. So one thing, however, that we did later after publishing our model was that we played with numerical prediction data as conditioning for forecasts at a longer horizon. And that combining, for instance, the rain flux, which is a deterministic forecast of rain from the numerical prediction model, with radar at a longer horizon worked pretty well. Okay, so that's a long explanation of something we didn't use, which is numerical prediction models, but which are an extremely useful and needed tool for longer and mid-range weather forecasts. Then there is, and this is here a plot of this rain flux, which is the forecast of rain from NWP. Then there is rain gauges. So we didn't use rain gauges because the data was messy. So we just use it for some calibration or investigate it for validation, but it was difficult to make use of it. And finally, there was orography and land cover, which we thought were vital, but actually ended up not being needed. And we believe that this is because of conditional independence given radar measurements. Orography and land cover essentially ended up being explained away in the prior information of existing rain, especially rain over mountains, which is very noticeable. When you look at rain over mountains, it's almost like watching stationary rain and then a moving component on top of it. It's an interesting phenomenon. And that you can basically, if you just sum up radar over time, you recover orography, which is elevation. And finally, I should have mentioned, we didn't use satellite data, unlike the MetNet study, simply because we didn't have access to data over the UK. But it proved, again, not necessary to get good results. Okay, so we just finished the first step, which is introducing the problem. Now I need to say a few words about the baselines. So the first baseline what we looked at was so-called STEPS, which is the open source system used by the Met Office, and relied on their open source Python library called PYSTEPS. It is an industry standard model for probabilistic precipitation nowcasting, which relies on multi-scale optical flow. So the optical flow is estimated from the most recent consecutive radar images with some smoothness penalty. And this is used to define a 2D motion field called advection field. Then using that advection field, we can extrapolate using semi-Lagrangian extrapolation the most recent radar images to make predictions in the next few time steps. And because of the application of a stochastic perturbations of rainfall intensity at the beginning, before that extrapolation, we can obtain different realizations for ensemble nowcasts, essentially using the same principle as in numerical weather prediction models. And that means that we can derive both probabilistic and deterministic forecasts at multiple spatial timescales. So early in our research, we try to improve upon the optical flow-based methods by trying to learn a differentiable approach to optical flow. And what we did was use state-of-the-art PWC-Nets, as in pyramidal warped cost volume networks. And they work well for learning to estimate optical flow from sequences of consecutive images without labels. So here we run into a problem: the boundaries of the image, where information is missing, and where the neural network finds creative ways to make up predictions, basically smudging the edge of the image, which is not physically plausible. So of course, you can circumvent that problem by having a wider image from which you do the estimation of a field, and that you advect. So the process, so that translation and actually the affine transform for the optical flow is called the meteorological term advection. And then only look at the center crop, but still there's something unsatisfying in the fact that the PWC-Net learns a very strange optical flow that basically just smears out the edges of the image. So yes, so actually here I'm illustrating again the point I just made. So our PWC-Nets surface the workaround, but we use throughout our research, which is we let the models make predictions on a wider area. So let's say 256 by 256, but we optimize the loss only in the central area, the central crop, let's say 64 by 64. And this avoids to have the biasing effect of wind-based advection. And we based our margins on the assumption of a wind speed at 60 kilometers per hour, which is 60 pixels per hour, and 90-minute forecasts, which means a margin of 90 pixels on each side. So here actually we had 96 pixels of margin on each side when we use 64 by 64 central crops and 256 by 256 images. Okay, so our second strong baseline was the UNet encoder-decoder model, which is used by several of our colleagues and actually pioneered by one of our colleagues at DeepMind for medical image forecasting. Yes, so here, after extensive exploration of UNets, we made some architectural and loss function changes to improve the performance of UNets at a longer lead time and with heavier precipitation. What we did was that we replaced all convolutional layers with residual blocks, and we used 6 residual blocks that provided a small but consistent improvement across all the prediction thresholds. Also, we would predict only a single output and use autoregressive sampling during evaluation initially, But then we realized that we got better metrics when we let the model predict all frames in a single forward pass. And that would try to mitigate the problem of blurring that is often found in literature when you try to do time series prediction using deep learning models. Not time series, but video prediction using deep learning models. And this improved results on quantitative evaluation. And yes, I should say that we used both regression and classification losses for the UNets. However, we still had a problem. Even though UNets would outperform traditional optical flow in terms of metrics, they would still produce blurred predictions. And the forecasts will typically get a little bit fuzzy over mountainous areas, for instance, Scotland or Wales, where there are more mountains, and where there is orographic rain, or on the coast. And one could barely distinguish the front of a forecasted rain, which is still important for meteorologists. So we tried to get an even better baseline and model, and that's where our colleagues at Google Research came in a lab led by nowcasts. They published in early 2020 the MetNet model, which was a very strong state-of-the-art baseline for us. MetNet is a combination of a convolutional long short-term memory encoder and an actual attention decoder. It has been demonstrated to achieve strong results on short-term up to 8-hour low-intensity precipitation forecasting using both radar and satellite data of the continental US. And MetNet makes per pixel probabilistic predictions, and it factorizes spatial dependencies using alternating layers of actual attention. So what we did is that we adapted the actual attention model underlying MetNet to our specific setting by paying attention to have a strong competing baseline. And in our study, we operate at the same scale as the original MetNet implementation, which is 1 kilometer per pixel for UK data and 0.01 degree per pixel for US data. And we make predictions at a shorter horizon of up to 90 minutes. Because we assume rain cloud maximum speed of 60 kilometers per hour, we could reduce the margins to 96 pixels. And so we could use only 256 by 256 inputs with 64 by 64 outputs. And for this reason, we didn't need an extra downsampling module that was used in MetNet. We also reduced the temporal extent of the input context from 7 frames, which were covering 90 minutes, with 15-minute intervals in the original MetNet implementation, down to only 4 frames covering 90 minutes with 5-minute intervals. And we didn't have access to geostationary satellite data from the UK, so we conducted our study using only elevation, position, and time embeddings in addition to radar. But counterintuitively, we observed that this additional elevation, positional, and temporal embeddings did not improve performance, and changes in metrics were not statistically significant. We hypothesize that at the time scale at which nowcasting operates, the phenomena represented by those additional embeddings were modeled in the dynamics of precipitation over 4 input frames already. We rescaled the targets of the model to improve the performance on forecasts on heavy precipitation events using sampling from the data set. But this didn't really help that much, even though we managed to get very good performance in terms of metrics. And I will go back in details to those metrics and keep talking about. There was a problem. The predictions were still blurry. So what is the problem behind those blurry predictions, and why we actually need generative models and uncertainty? So I'm going to explain the problem in 3 different ways. And the first one, we're making an analogy to language models, something I worked on a long time ago. And those language models are, by construction, autoregressive. So here I actually played with the latest language model by DeepMind called Gopher. Well, Actually, there is even earlier one that's just been released called Chinchilla. But I used Gopher. It was published a few months ago on Archive. And I fed the following prompt to the language model. Precipitation nowcasting, the high-resolution forecasting of precipitation up to 2 hours ahead, supports the decision-making processes. So each of the word tokens that is generated here is generated by sampling from a probability distribution of the possible tokens. So for simplicity, we suppose that these are word tokens as opposed to character diagrams or other kinds of presentations. And a different realization with the same prompt and the same context could be increasingly important issue of flood. So every time the language model generates a token, it feeds it back autoregressively as context for the next sample. And these probability distributions are calculated on the fly during the generation. So a third realization could be effective planning of emergency response. And importantly, these probability distributions of the words are not computed jointly, in parallel and ahead of time. You don't have a logit for each pixel that's computed by a single model at the same time, because it would not make sense to sample independently the words, increasingly planning processes using independent sampling processes, effectively. You need that sampling to be autoregressive, just like in models such as Pixel or NN, which are autoregressive. And that was actually the problem with the MetNet problem, the MetNet, sorry, the MetNet model, which is that it generated logits for all the pixels at the same time. And then it typically, the model would be optimized using a loss of a multinomial loss of all the pixels at the same time. So you just add the sum of losses for each of the pixels. And generation would consist in taking the mode of a predicted distribution. But when we try to sample from that, it didn't work at all. So now, how does language modeling and generation relate to our problem of precipitation nowcasting? Okay, I think I just said that. So UNet and MetNet, the models I described earlier, were making the following assumption for modeling the optimization objective. Joint probabilities over all horizontal and vertical pixels of a generated image. In some cases, computed for all time steps at the same time. And that means poor assumptions about conditional independence given the context. And the optimization process optimizes the mode of a distribution, but nevertheless assumes conditionally independent Gaussian probabilities for mean square error regression, or conditionally independent multinomials for classification. And this is what conditional dependence assumptions boil down to in the case of two grid cells. Let's say the orange and the green one here on the graph. If we are given the context input under the conditional independence assumptions, then knowing about the value of a green grid cell does not help us make a better prediction of the value of the orange grid cell. The input context factors out the conditional probability. But yet, those two are related because of spatial correlations and their proximity. And the problem is that even if we manage to train UNets and MetNet, and they get good performance metrics, we cannot actually sample from those distributions. And that's a problem, but once we acknowledge that the weather data is inherently stochastic. So I'm going to explain the problem a third time, but this time with a thought experiment that we initially thought about adding to our supplement in the paper. So imagine that there is a precipitation front that is moving, and that is very localized, and that is very strong, 30 millimeters per hour. So you really get drenched if you get outside. And that precipitation front could move towards London or towards Brighton, which is on the coast of England, not far from London. So that means that at time 0, our estimates of the probability of a rain in London at time t plus 30 minutes is 0.5, and the same for Brighton. However, at time t plus 30 minutes later, we observe that it is raining in London. What does it mean about rain in Brighton? So because we have a very localized precipitation front, we could have a very localized, there could be no rain in Brighton at all. Actually, there would probably not be no rain in Brighton at all because the rain has moved to London. So the problem with the conditional independent model is the following. The regression model will say it will rain at a rate of 50 millimeters per hour, both in London and in Brighton. And because of uncertainty, it is blurring the rain over the two cities. This is literally what the traditional regression loss is telling the model to do. And the classification model will say that it will rain 30 millimeters per hour, with probability 0.5 in each city. And this could mean 4 different things. Rain in London and rain in Brighton, 1. Or 2, rain only in London. Or 3, rain only in Brighton. Or 4, sunshine in London and in Brighton. Each of those has a probability of 0.25. And of course, it doesn't really make sense. And this can lead to wrong estimates of accumulated rain, which is prejudiciable for flood forecasting, one of the objectives of our study. So the problem is that both those estimates have critical success index, which is a metric I will define in the next few slides, of 0.5, which is actually good. So how can we fix both the model and the evaluation? So what went wrong with the baseline model is that it directly predicted grid cell-wise or pixel-wise rain rate probability, and that it was trained discriminatively with a conditional independence assumption. It was optimized as each pixel location from the point of view of someone with a garden, let's say, and who wants to know if it will rain over their garden, over the pixel where the garden is located, but without taking the whole picture of rain across the whole country into account. Whereas meteorologists care about the bigger picture, even if they want to provide good estimates for each individual location. So what we need are generative models that produce plausible realizations of rain and that can derive statistics from those realizations. Okay, here I forgot to move ahead with the slides, so I'm just leaving that slide a bit visible for a second or two. And now, moving on. So how do we model that uncertainty? Using generative models. So as I have motivated for half this talk already, we would like a model that is consistent across spatial and temporal scales, and that captures rare events, and that properly accounts for uncertainty. So basically what we want is a sort of a neurosampler that generates multiple realizations for a given prediction. Just like the numerical prediction models I spent a lot of time talking about at the beginning, or steps, PYSTEPS, the optical flow with initial perturbations that is used by the Met Office. So because we have those multiple realizations for a given prediction, we can calculate the uncertainty of those predictions from those realizations. And that's why we settled for conditional generative adversarial networks. And here we are building upon the work of our colleagues who previously published Big GAN for generating images and DVD GAN for video prediction. And there are some links on arXiv here. So generative models are very popular as a class of algorithm, and they learn to approximate the distribution of observed data X and to generate samples XS from that distribution. They are built using a deterministic model like a neural network and incorporate stochasticity through a latent random vector Z. When fed with a random vector Z sampled from a multivariate Gaussian, they generate samples from the learned distribution. Conditional generative models predict a realization XS, conditional both on the latent random vector Z and on a conditioning variable Y. Variable y could be past radar estimates of surface precipitation, and variable xs could be a future instance of radar fields. And a specific type of generative models, called generative adversarial networks, relies on adversarial training to train both the generator and the discriminator between the output xs from the generator, called fake, and any target image XR taken from the dataset. 4 consecutive radar observations covering the past 20 minutes are used as context for the generator, and they allow sampling of multiple realizations of future precipitation, each realization being 18 frames and covering 90 minutes. During training, the generator takes inputs that are 256 by 256 pixels and outputs 256 by 256 frames as well. Learning is driven by two loss functions, and a regularization term. The first loss is defined by a temporal discriminator, which is a 3-dimensional convolutional neural network that aims to distinguish observed and generated radar sequences, imposes temporal consistency, and penalizes jumpy predictions. The temporal discriminator takes a random 128 by 128 crop out of the generated or real radar image. The second loss is defined by a spatial discriminator, which is a convolutional neural network that aims to distinguish individual observed radar fields from generated fields, and it ensures spatial consistency and discourages blurry predictions. The spatial discriminator takes a random set of 8 frames, either real or generated, and subsampled by a factor of 2. And there could be a trade-off between the two adversarial loss functions, spatial versus temporal, in the GAN, but we didn't really spend too much time optimizing that trade-off, and we simply kept the relative weight of 1 for the two losses, spatial and temporal. Then, to improve accuracy, actually to enable accuracy, we need to introduce a regularization term that penalizes deviations at grid cell resolution between the real radar sequences and the mean of the predictions given by the model. So what we do is that we generate multiple samples, multiple realizations, and then we take the mean of that, and we compare that mean to the actual target, what rain actually happened based on radar images. So now I called this loss function as a regularization term, but actually I think we should think of this as the primary prediction objective. And the two GAN losses should be seen as the real regularization terms that enforce spatial and temporal structures. And those two discriminators share similar architectures to existing work in video generation. So now the generator. Let's go deeper into the generator. The generator comprises a conditioning stack that processes past 4 radar fields, which are used as context. And this conditioning stack allows information from the context data to be used at multiple resolutions, down to a map that is 8 by 8. And it produces a context presentation that is then used as an input to the sampler. The sampler that generates those images is a recurrent network formed with convolutional gated recurrent units, GRUs, that uses the context and the latent presentation as inputs. The sampler makes predictions of 18 future radar fields, so the next 90 minutes, autoregressively. That's why it's a GRU. And the output of the conditioning stack can be seen as the initial conditions for the sampler. And the sampler needs a source of stochasticity, which comes from the latent conditioning stack, And that latent conditioning stack takes samples from a Gaussian distribution covering a spatial 8 by 8 map, because that's how we train the GAN. And we reshape that noise into a second latent representation that is then added at every time step to the conv GRUs of a sampler. These additional latent variables are what enables us to account for uncertainty. So they essentially are the equivalent of those stochastic perturbations. And interestingly, those stochastic perturbations happen not only at initial conditions, but also during iteration of the sampler. Okay, so
I think we have a question here from
yes, that's very good. Take a breath.
Let's go back a slide. I think it's one slide back. I also want to see that I understand the question. So he's asking, you use attention module when transforming the random noise vector in the latent conditioning stack. What is the purpose of this layer, and have you tried not using it?
Yes, the attention model. So it was basically that's work that was led by Carol Lenz from the team. It was empirically found to work better. Yes, I think that is a very unsatisfying response. Yes. And I think
that's the trend right now using this method.
It essentially enabled to provide some more spatial dependency in the conditioning.
Says okay, thank you.
Thank you. So we train and we validate the model on the random sampling of crops from the radar from 2016, 2018. And what you see here on this slide are random 256 by 256 pixel crops, but are samples taken from a data set with high precipitation values, because 95, sometimes even more, % of the data is uninteresting. It's just a white picture without rain. So those samples are not as frequent as you might think, right? As I just said, even if the UK is seen as a rainy country, typically. So we have split the data into grids of 256 by 256 slices for processing at training time. But we can actually use much bigger inputs for testing. So the whole UK data set covers the whole UK and parts of Ireland for years 2016 through 2019. And in one possible split, the weekly split, we can train on Mondays, Thursdays, Fridays, Saturdays, and Sundays for about the 4 years, and validate on Tuesdays and test on Wednesdays. And as an anecdote, the experts from the Met Office told us that there is a barbecue effect apparently happening on weekends. So we needed to, that's why we chose Tuesday and Wednesday for validation and testing instead of Saturday and Sunday.
Can you elaborate?
Well, that's just what they said. Basically, there are more aerosols. There may be more aerosols in the air during the weekends because of barbecues.
Really?
Yes.
Wow.
It's incredible. Now, another split, which is the yearly split, we train on 2016 through 2018, and we test on 2019. And we report results on the yearly split in the main paper that we wrote. One nice aspect of using the yearly split is that we avoid any causal and data leakage issues. Because we are certain that we really train on the past and predict in the future. However, we also reported the weekly split results in the appendixes of our paper. And there is a rationale for that, which is that we can imagine that the forecasting system could be retrained frequently on a rolling basis. Essentially every day, every 2 days, as it gets new data. So retraining on a rolling basis is a very good baseline, but of course it's a bit more involved and expensive as an experiment. So at training time, we used, as I mentioned, an important sampling scheme to create a data set that is more representative of heavy precipitation and that enables us to capture rare events. And we evaluated our model on a test set from 2019. Because the model is fully convolutional, we applied it out of the box. We could apply it out of the box onto much larger radar frames that it was trained on, covering the whole of UK or the whole of the US on MRMS data that I mentioned earlier. Both the radar conditioning stack and the latent variables conditioning stack are convolutional, and that allows to train on small crops while having spatially temporally consistent predictions during evaluation on larger frames. Unlike some other methods like MetNet, we didn't need to tile and to stitch small predictions to cover the whole frame. And importantly, once trained, our model allowed fast full resolution nowcasts to be produced in about a second using an NVIDIA V100 GPU or 25 seconds on a CPU, which of course compares to the several hours needed for data simulation using an NWP and actual radar observation data. So there are lots of gaps and also questions at this point, and I will try to. I can also follow up later by email. Just checking the time. So I've been talking much. I think I've actually been taking my time. So are we still good with time? We still have like 20 minutes.
For sure, we do. Yeah, we even have a bit more if we need that. Not an issue.
Perfect. Yes, fantastic. So now we're getting into the quantitative verification and the limits.
Maybe before, you know what? I think some of the audience this is their space. It's not mine. But for me, the interesting question here will be: so the benefits of convolution you've mentioned. What is the downside? Is there a downside? I don't think translation or rotation is an issue here, but are there other stuff that we miss because we're using like convolutional window analysis?
Yes, that's a very good point. This is not something we report in the paper, but we noticed that the UNet was actually failing to do simple advection by 1 pixel sometimes. So essentially we divide, in the earlier phase of our experiments, we're really working on architectures, and we investigated, for instance, attention models, like the actual attention, or specific optical flows-based methods that predicted a field to advect an image, because we noticed that UNets sometimes failed some unit tests where we would have some very simple, obvious translations that didn't fit exactly in with the size of a convolutional kernel of a unit.
Mm-hmm.
So there are some limits to the translation invariance of those convolutional models.
I wouldn't think that was a problem, actually. I would never imagine. Okay. And can you repeat again? How did you solve it, and how were you able to solve it?
Well, so basically, the architecture that is used in the GAN is more geared towards it effectively does something a little bit like a prediction of a field.
Okay.
Yes.
And maybe it's a question of ignorance, but why does this help more? Why does it solve it, or what was the idea behind using it to solve the problem with small translations?
So essentially, if you learn to predict a field, then you embed an inductive bias in your model about the fact that the future prediction is a deformation of your context, rather than having to basically, if you just have a pure UNet architecture, you need to learn a translation at the level of each convolutional kernel in the encoder and decoder. Whereas here you learn to predict small values of or larger values of translation for a field, and then you can take your input image and translate it.
Okay, I think maybe I will need to look back at the recording to figure out completely. Not entirely thinking, but this might be on my end. I need to look back at the information again. Okay, I had a remark, but I want to clarify before I mention it. So that process you went through with recognizing the limitations of, let's say, if you're doing a statistical assumption that there is independence in the data, but there is none actually, and then you're using the different discriminators to solve for that independence is quite cool for somebody coming from statistics, because this is not something you can solve when you're doing classical statistics. But then with deep learning, you can try, even though we don't really assume these assumptions of independence when we're working with deep learning, using like those limitations in the network architecture itself is quite cool. Trying to figure out where else it can be used. Probably I'll think of it and I'll mention later.
Yeah, I mean, for me, the most obvious example for me was language models, but yeah, modeling sequential data. So the evaluation of generative models. So the advantage and main limitations of generative adversarial networks is that they generate realistic images, and that can be very misleading in many ways. And in our initial work, where a bit of some of the ingest, we actually showed meteorologists samples of GAN-generated forecasts and real observations, and asked them to see if they could guess which was which, and to see if they could be fooled by the model. And we noticed that the confusion was easier when we were predicting a single image rather than when predicting an animation of longer-term predictions. But that so-called Turing test was not interesting per se, because our objective and metrics are not to produce realistic images, but rather to produce actionable forecasts. And actually, as an anecdote, the GAN is so good at imitating reality that it's capable of generating radar artifacts that look like radio spokes coming from the radar location, and in the video over time end up looking like flickering, which could be due to birds or planes or other obstructions passing on the trajectory of a Doppler radar. So the GAN learned to generate those artifacts, which of course doesn't make sense. So the first metric under consideration was critical success index, CSI, which measures the location accuracy of the forecast at various rain rates. And here I'm showing 1, 4, and 8 millimeter per hour. It's a ratio of true positives in the numerator to the sum of true and false positives and false negatives in the denominator. And it also corresponds to the Jacquard distance. And we can see that all three deep learning systems, UNet, Actual Attention, and our generative model, produce forecasts that are significantly more location accurate than the optical flow-based PYSTEPS baseline, which is in green. But what we know is that UNet and Actual Attention make blurry predictions, and yet CSI does not account for all those different ways a model can kind of cheat to score better. And so that's when power spectral density becomes useful as a metric. Here, those power spectral density plots show that both our model, the GAN in blue and PYSTEPS in light green, match observations, black dotted lines, in the spectral characteristics. And PSD plots also show that predictions from UNets have much less small-scale variability, which means that they are smoother or more blurry, and that this gets worse with increasing prediction horizon. And to the contrary, predictions from actual attention and from MetNet have a lot of small-scale variability when we do sampling. And this is due to high-frequency noise during the sampling process, and I will get to that in the next slide. So all these models produce blurred predictions in the average, and the effective resolution of the actual attention and UNet and nowcasts is therefore less than the 1 kilometer by 1 kilometer resolution of the data. At t plus 90 minutes, the effective resolution of a UNet is 32 kilometers, and for actual attention is 16 kilometers, if you just take the mode of a distribution. And that reduces the value of nowcasts. Please.
May I have a question? Sorry. So like, thing that I'm interested the most is the comparison to the extreme events,
Yes.
the highest precipitation. I don't know, maybe you're going to talk about that soon. And do you have some comparison to non-machine learning models? I don't know, NWP or something, because basically what I observed in the work that we did is that machine learning, deep neural networks, they tend to smooth the areas. So like, you know, so they tend to struggle a lot to get the extreme events. And I'm really curious, you know, to see some discussion about that.
Yes, yeah. So yeah, we will get to that. Oh yeah, sorry, I forgot to go through the build-ups. So yeah, so here I'm illustrating where the blurriness happened, and also the high-frequency noise when you sample from actual attention using independence assumptions. So before we go to probabilistic results, here this is the ensemble variability of GANs samples for 6 different realizations and at 3 different time steps: t plus 30, t plus 60, and t plus 90 minutes. And so you can see that the differences between realizations are rather small, which is kind of reassuring. And that's the beginning of the answer, Grzegorz. Yes, Grzegorz. Got it, of course. So
I thought you're Polish, you know, should be easy.
Yes, exactly. So the essentially a model like GAN could dream up rare events more frequently, but of course the problem is that it could dream up those events at the wrong location. So you still need to be very careful about the uncertainty here. But at least there is a possibility, and that can be informative for meteorologists, that this model could perhaps dream up a possible rare event, which of course needs to be taken with a grain of salt. Yes.
Is there like, do you have anything like in mind that could improve it? Like, probably the easiest would be, of course, like assuming some samples to those high events that you have in the data set, but they may like destroy the bias. But I don't know, do you have anything in mind that could help that, or?
I can't, and if other than the combination of more data, more recent to take into account non-stationarity and drift, maybe some, basically just more information. Now you're just using radar, but if we actually had other meteorological information like CAPE or humidity, temperature, this could be much more useful for forecasting convective initiation of all those rain cloud formations. So more data on different, more physical data, some physical inductive biases, maybe in the loss function, and just more data. Yes. Sorry.
Just one more question. Like, so here for me to understand, so like as an input you take like multiple just precipitation radar or that MSR. How many of them do you take?
Oh, we take 4.
4. So it's like every 30 minutes. That's what the difference.
Every 5 minutes. So we take 20 minutes 4 frames, which is at the same time scale as the predictions, which are also every 5 minutes. We make 18 predictions every 5 minutes.
did you think about taking longer period, or it was like
Longer the past? Yeah, so we compared 4 versus 6, and we didn't see a big difference in all the metrics, so we just stuck to that.
okay, like that's why I'm asking, because like, you're not using NWP as a part of the predictor, so that's why I thought, maybe longer. Okay, thanks.
Yeah, but if we used if we use NWPs as inputs to predictor and also driving future predictions,
Yes.
As an additional input, basically, then it really or just fed through the conditioning stack, that definitely helps a lot, of course.
May I maybe have one more question as well?
Please,
okay, so what I'm wondering is at the previous slide you were showing some metrics, and my question would be, how did you what was the data that you actually measured those metrics from? Was it like the expected value of those metrics, or did you choose some representative sample that you measured on, or how did you choose this?
Oh, right. Yes. Okay, so I'm looking at power spectral density, for instance, or CSI.
Mm-hmm.
Yes. So I think so for UNet, MetNet, you have a single realization.
Mm-hmm. Yeah.
For the GAN, we used, I wonder if it was a single realization for deterministic metrics like CSI, and then an ensemble of realizations for probabilistic metrics.
Mm-hmm. Okay, I see.
And I would need to check the paper. I wonder if there were. I'm not sure. At this point, I'm sorry. Because it's been a long time. I'm not sure if those plots are based on the average or based on a single sample. I will come back to you.
Okay, thank you.
Okay, so those realizations that I showed earlier for GANs differ less from one sample to another than the ensemble baseline used by MetOffice, which is the optical flow baseline, where there's more variability. And we also tried, and that's what I mentioned earlier, to sample from the logits of MetNet, of actual attention, to obtain similar variability estimates. But however, the problem here is what I introduced earlier, was that we were sampling independently from those logits behind every pixel in the predicted image. And because we are condition independent, so is the sampling process. And if you sample from a softmax applied to those logits, even with a fairly low temperature of 0.5, you essentially generate uncorrelated noise instead of different plausible realizations. So that noise was what was driving the power spectral density. So now getting into probabilistic verification, we use continuous rank probability score, CRPS, which can be seen as the difference between two expected values. The difference between the observations and generated, and actually the mean of a generation, and the expected value of the intrasample noise. Sorry, yes, the difference between two different realizations. And so CRPS, yeah, so difference between mean error and the mean intrasample variability. It's computed on the average precipitation rate, right, across different realizations and aggregated over regions of increasing size. So we measure CRPS at the grid resolution level, and DGMR, our method, PYSTEPS, the optical flow, and actual attention perform similarly. But as we increase the spatial aggregation, the generative model and PYSTEPS provide consistently strong performance with the generative model performing best at maximum precipitation, the rare events. Whereas the actual attention model is significantly poorer for large aggregations and underperforms other methods aggregation scale 4 km and above, even if you try to scale outer probabilities.
Can
Yes.
I have sorry, for me just to understand, because you predict one single value, not the distribution here, the network, or how that CRPS is calculated, because how I understand to CRPS is that you would predict the distribution and you would have a single value and then you calculate the CRPS. But here you predict the single value, yes, and you have the probability of that associated with the value, or
right. So basically the GAN. So for the GAN, it generates multiple realizations.
oh,
so the second term of CRPS is the mean difference. Between different realizations.
But you do not calibrate the model, like let's say in terms of the probabilities, yes, or
sorry,
you do not calibrate the model in any way, to optimize to have the true probability of accidents, the value, or it's just whatever model gives you. Is that what you use here in the CRP?
Yes, yeah, I think so. Yeah. And in order to actually, no, sorry. No, there was a calibration. No, we did calibrate on validation data, actually. Yeah.
Okay, so basically you have the additional layer afterward that calibrates just the probabilities, and that's what we see here.
Yes. Yeah.
Okay. Okay, thanks.
Yeah, we did. Yes, we did. Yes. Yeah, and so for the GAN, it's the different realizations. For optical flow, it's again different realizations. And for MetNet actual attention with different samples, which are treated as different realizations. So now we can look at a case study, a single case study that compares nowcasting performance of different models. So we'll here look at a small, slightly more difficult case chosen by the Met Office chief forecaster, who was independent from the project team. And that case focuses on convective cells in eastern Scotland, with some showers over land. And traditional methods like PYSTEPS try to apply optical flow, but also overestimate rainfall intensity over time, which is not observed in reality and doesn't sufficiently cover spatial extent of rainfall. The UNet model predicts location of rain, but has an aggressive blurring and overpredicts areas of rain, misses intensity, and fails to capture small-scale structure. And the same happens for actual attention. But when we try to sample from logics of actual attention, feeding them through a softmax, after calibrating temperature on the validation set, so we add unstructured noise, but do not improve spatial details. By comparison with a GAN, we can preserve spatial structures and we can represent the convection events well and maintain heavy rainfall in the early prediction. So we verified our study with MRMS data coming from continental US, where prediction errors were slightly lower than the UK, both on deterministic and probabilistic metrics. And we noticed that there were some differences in US regions. So we didn't conduct highly specific case studies in the US, but we looked at general comparisons and spotted differences between Pacific Northwest, Midwest, and East Coast in terms of complex and small-scale rain formations, which were analyzed in terms of power spectral density. We also evaluated the contribution of different combinations of losses on the tested performance. For instance, using only grid cell regularization loss in violet without discriminator losses. We noticed that this led to better results with regards to per grid cell CSI, but also led to significant increase of CRPS metrics and unfavorable spatial frequency, power spectral density characteristics, meaning blurry predictions. So now, when we showed these forecasts to expert forecasters, meteorologists, they preferred predictions made by the generative model. And the case study highlights a limitation of existing metrics to evaluate forecasts. Those metrics implicitly assume that models such as NWPs and advection-based steps preserve a physical plausibility of forecasts. Deep learning does not incorporate physical knowledge and is much more flexible, and it can gain these metrics and outperform those other systems that are physical in a creative way, but still fail to produce useful predictions. So that brings us to the expert evaluation. So here we designed a new type of controlled study of expert judgments to assess the performance of nowcasting methods. We assess the performance of the preference, of 56 mid-office expert meteorologists confronted with those models and the results. We worked with the mid-office chief forecaster who did not participate in the design of the study, in the study itself, but he helped us to design the study, and he helped us adjust the type of assessments. The study itself was submitted to ethical review by an independent ethics committee that included an external review board, and the hopes for our approach were that using expert verification would provide us with insight into the usefulness of machine learning in an operational setting. Could it inform decisions on the development of new machine learning approaches for nowcasting? So the experimental protocol had two phases. The first one was about preference ranking of predictions coming from three sources. Participants were provided with a user ID before the experiment to preserve anonymity, and they were shown a total of 23 cases of high precipitation data over 5 millimeters per hour, selected by the chief meteorologist in the following format. Observations at T+0 with date, time, and geographic context. And in the middle, ground truth at T+30, T+60, and T+90 minutes. And 3 comparative approaches to nowcasting at T+30, 60, and 90 minutes. The optical flow-based system used by the Met Office, STEPS, a deep learning baseline, which was the actual attention model, and the generative model, always placed in a randomized order. And there was a color map scale for reference. And on the right, there is a form. The participant was asked to rank the model predictions compared to that known ground truth. They could also leave comments. So the operational setting, forecasters would often use multiple sources of information to make decisions, but here we opted to show radar-based plots only with limited additional information to ensure we can limit and control experimental variables. We also deeply thought about the phrasing of a question, and we used a social science study approach to design the protocol. After that study, in phase 2, a sample of participants were selected at random to complete a retrospective recall interview, where they were asked to review rankings from phase 1 and to review the decisions that they made. During that interview, the researcher who was running the interview tried to build a picture of a cognitive process for decision-making and finding out what were the important features. Recall of a task, details of emotive reasoning behind decisions, and blanks, mistakes. That researcher would take notes during the explanation of the participant. And we had pretty drastic results because most forecasters selected the proposed generative method as the most preferred, with the next most selected being the existing STEPS model for the Met Office. And the key factors included the ability to capture the extent of rain, even when intensity wasn't quite right. And these results contrasted with the qualitative verification scores that didn't give enough indication of difference between competing approaches. Those results contrasted with the quantitative metrics that I showed earlier, yes. Because those metrics didn't, they often favored models that blurred forecasts over time, instead of models that provided a good picture of rain at a geographical spread. So we have some examples of what the meteorologist said during the interview, some of the quotes. And yes, in summary, we're pretty happy about running this operational assessment, and we think that it's the kind of methodology that can inform how we run experimental psychology studies in atmospheric sciences and how we gain insight into meteorological decision mechanisms. And this operational driven design was aimed at ensuring that machine learning based products can deliver value in an operational context. So reaching out to the conclusions, nowcasting fills a gap in performance of numerical weather prediction models in the first 2 forecast hours. It highlights a role for machine learning to be complementary with existing physics and driven and simulation-based approaches. We are not interested in replacing human expertise. We're interested in empowering human experts with useful tools. Deep generative models like GANs can improve upon deterministic nowcasting methods. They are able to provide probabilistic ensembles required to estimate the evolution of chaotic systems. They're also suitable for high-intensity events. For instance, knowing the uncertainty precipitation nowcasts can be used for estimating the quantity of rain accumulated over a catchment area. So that means that even if you do not predict precisely the location and time of a random event, you can still look at how it accumulates over a wider region, which is important for flood forecasting. And finally, looking ahead for our future research on long-term weather forecasting, we want to keep the human in the loop. We want to provide genuine decision-making value for real-world experts. So yes, we built a deep learning model that is preferred to operational system by professional forecasters, and we hope to keep building useful models. So at this point, I'd like to thank everyone for your attention and all the questions that you asked. You can play with a trained UK model with corresponding data and Colab. The Nature paper website has a pseudocode also that is attached to it. And I would welcome any other questions from you at this point. Thank you again.
On YouTube, there are none. If anybody here, no, I think also on the chat. No, I think, oh, there you go, Reed. Go ahead. Oh, it was just
no
a
questions.
raise of a hand.
Thanks for the presentation.
So I am now checking basically the paper about the, yes, so the very important question. So actually for deterministic metrics, the like CSI, we still used 20 samples from the GAN, which means that we took the average of 20 samples. Yes.
Okay, thank you. Then it answers it.
Yes. And in a way that does make sense, because during the optimization, the loss term was taking the mean of realizations as an optimization objective. Yeah. And so what we noticed is that if we removed the GAN losses, so we just basically trained an autoregressive model with some inductive biases on how the flow is treated at every stack, every level of a stack. We obtained a fairly, we essentially had a model that was blurry, but very good on the metrics. Yes. And without a spread. Yeah.
Maybe one more question then. Have you tried playing, because you use basically weighted L1 loss in the grid cell regularizer, right?
Yeah.
Have you tried, because I know you're clipping there for precipitation up to 24, and you also like you do y+1 and clip it to 24. Have you tried using different values for those to wait for even heavy rain or low rain, or were those
Yeah.
that you settled for from the start?
Yeah. So I think it was not only L1, it was, I think it was, I wonder if it was L1 and L2. Maybe there was only one, mean approximate error. Or at least at some point we considered using a mixture of L1 and L2. But yeah, the weighting happened. The weighting was basically by precipitation level itself, which means that we give a higher loss to rare events and higher precipitation. And sorry, when your question was, did we try to even weight even more?
Yes, because you add 1 to the observation to account for, basically to still punish predictions that have no precipitation, if I'm correct. That's the assumption.
Yes.
But have you tried to like adding more to it so that you weigh even lower precipitation higher, or have you tried lowering the maximum cap to weigh the higher precipitation lower, so that it would, like, if it did change something, or if you tried it, or if those were the values that you settled for from the start?
No, I think that this is something we investigated at the beginning, but we just we just stuck with the design choice. Okay. I mean, we looked at a lot at classification losses too, because that, of course, that. So here, for one of the questions was actually, how do you design the bins? But we noticed that somehow UNet trained with classification loss didn't perform as well, even after heavily optimizing for the best, like using a mu law reweighting, and we didn't really achieve better results with classification losses as opposed to regression losses.
Yes, I guess the reason why I'm asking is because we are trying to train a little bit less robust model because of hardware issues, I would say, because you probably know that the model that you proposed does take a lot of memory, in fact.
Yeah.
And what we noticed is with those values, for higher precipitation, it does pretty good forecasts, but it tends to almost forget about the low precipitation fields because it doesn't. It seems to not do that, and it might be just because the model is not trained enough. But what we also experimented with is if we increased the weighing of the low precipitation, that it did put it there, but then it was not trying to do the predictions of the higher precipitation. So that's why I was asking if you have experimented with it or not. But yeah, okay. Thank you for answering that.
And you're using a generative model?
Yes, we are using basically the same architecture, but we just reduced it by reducing the number of channels in various components of it, so that it has basically less capacity.
Okay.
For those of us who didn't run it, how much memory are we talking about, and also what type of hardware in general? What type of GPUs? How many?
We are training it on 2 RTX 390s, so it's taking 48 gigs of memory if we run on both of them.
And the original network, how much, Piotr, how much did it take you guys?
I mean, it was actually possible to train on, I mean, I managed to train in a slightly smaller version on 12 gigabyte on desktop, but debugging, but for like predicting 128 by 128, I think. But yes, the model would hold. I mean, I think the model will actually hold on the 100 during training. If I'm not, or maybe I'm.
This is what the ones we're running. It's taken 48 gigabytes, and we're only predicting 6 timeframes with batch size of 8.
Yeah.
So this is so it would take much more probably for your model.
Right. Okay. So I think so. Actually, I think okay, that's right. So because there is the size of the inputs and outputs, but also the number of time steps. Yeah.
Yeah.
Yeah. So basically, yeah, I was using the desktop to check if it was running, but then learning something, but then quickly switching to.
By the way, what are the training times, Piotr, on your machines, and what machines were there?
Yeah, so very quickly on, basically we switched to the TPU architecture, and so then it will be a matter of a few days. Yes, a few days, and well, let me. I'm going very well prepared.
These are the sort of questions that, like, personally, me, I always like to ask, because that's not what you read in the paper. But
Exactly.
like, if you try to implement, this is where you get stuck. So it's like this. Yeah.
Yeah. So it's I think one thing I can just try to check is the topology. Like the size of because I think yeah, the topology of a TPU is a good indicator. In a way, perhaps maybe one thing I can do is actually follow up specifically on those questions. Probably do better than just doing it live.
Sure. I'll add it to the like the YouTube and the recording. It will be in the description.
Yes.
Anybody else? No, maybe.
I may have one more question if anyone has there. So what was not in the paper, and what I was wondering, because of trying to implement the network, is how did the losses look like during training? Specifically like the generator and discriminator loss, and how did they look like? Because that would be interesting to see, I would say.
Mm-hmm. Yeah. Yeah. Yeah, very good question. To see basically if it learned to generate realistic samples first and then latched on to fitting the actual data, or if it was the reverse.
Basically, in terms of basic GAN network, the classical problem is how your losses look like generated to the discriminator, if they're like converging to the same value, or if there's any difference between them, like that kind of question, I guess.
Mm-hmm. Yeah. Yep. Okay. I will follow up. Yes. Yeah, because basically during training, I think, I mean, when I was running the experiments, so my contribution to this project was I worked extensively on the PWC-Nets, the baselines, and the MetNet baseline. And then I just used Toscaro, who did, and then Suman, who did the bulk of the work on the DVD GAN, so the generative model itself. So then I used invalidation, and I was basically using the total loss rather than looking at individual components. And then monitoring, actually during training, we're monitoring CRPS directly. Yeah, probably because, but maybe that's just because very early on we had, I mean, a model that kind of, we knew that what it worked about after about a couple of days, and so we just checked if it was, what kind of final value of CRPS it was reaching every time we run small changes.
Yeah, okay, thank you.
So I think we'll wrap up. Piotr, really awesome having you aboard and giving this talk. A lot of tough questions, I know, but I think we got a lot of value from it. Everybody in attendance and those who will watch the recording. Thanks all for joining. Sorry for that mishap with the Zoom link. Again, Luma is a new platform. I never used it before, so it's like beginning of it. Again, I think I sent out the links where you can find the community, all the discussions taking place there. We will be continuing running it. These types of online events are really hard for me to do. So for now, I will be scaling back on them unless there will be a lot of requests from the audience, and then we'll try to facilitate. I love having these events. So that's like, for me, it's like it's a bit sad to not have as many as possible. But yeah, again, thanks everybody for joining. Piotr, thanks again. Also, I wish everybody a good evening. I think most of the screens I see are with sun going down. So good evening or good afternoon. For me, it's already night. And until the next time, bye for now.
Super. Thank you so much for this invitation. It was it was great and nicely challenging. So I will follow up, and I will also ask Carol by email for all the details to help you.
Perfect.
With this.
Perfect. Thank you.